Let's talk about bars. No, not these kind of bars. Musical bars. A musical segment defined between two vertical lines. A bar contains a number of repeated number of beats given by the time signature. For example, this is 4/4. 1, 2, 3, 4. Or waltz, which would be 3/4. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. You can make the 4 main beats and subdivide them into 8 eighths of equal distance. You can go further and further, subdividing in 2s and so on, getting faster and faster notes into a single beat. But what if you wanted to include a number of beats that was not divisible by the time steps in your beat? For example, if you wanted to include 7/16 notes in your 4/4 bar, well, you could be lazy and just play them back to back. But that just lacks any interest, any musicality, any rhythm. Is there some intuitive manner that could make this a lot more interesting? If we take a regular 4/4 pattern, we can see that our drum hits are as equally spaced between each other as possible, creating this nice sense of rhythm. We could have just as easily placed them as close to each other as possible, as the hits are basically 16th notes, but again, it would sound atrocious. So, in order to fit 7/16 notes, we need to find a way to put them as equally distant from each other as possible. The Euclidean algorithm is a 2000-year-old algorithm for finding the greatest common divisor between two numbers. This is the largest number that divides both numbers without any remainder. For example, the greatest common divisor between 12 and 22 is 2, and of 6 and 7 is 1. The algorithm is really simple to do. Take two numbers, for example, let's take 7 and 9, we subtract the smaller one from the larger one, giving us 9 is equal to 7 plus 2, then we continue this operation subtracting the smaller of the right equation from the larger number. Thus, we have 7 is equal to 2 plus 5, 5 is equal to 2 plus 3, 3 is 2 plus 1, 2 is 1 plus 1, and 1 is 1 plus 0. And once you reach your 0, the algorithm ends. The other non-zero number is the greatest common divisor, in this case 1, as 9 and 7 are co-prime. Some of you might be more familiar with a slight reformulation of the algorithm, which makes use of multiplication to save a few steps. Indeed, that is much easier if you are good at multiplication and division, but the original Euclidean algorithm used repeated subtraction instead. Obviously, the two formulations are equivalent. What is the relationship between these two topics? Well, surprisingly, a 2003 paper found that creating such equidistant rhythm patterns is very easy to achieve if one uses the Euclidean algorithm. Let's take our beat pattern from easier, and for ease of representation, I will replace the hits with X and the empty beats with dots. This is equivalent to what we saw earlier and would sound like this in FL Studio. Here we have 7 hits and 9 rests for a total of 16 time steps. Remember the sequence from earlier of repeated subtraction? We will take the left numbers of each equation, which are always the smaller number of the two from the equation above, giving us the sequence of 7, 2, 2, 2, 1. We will apply the following algorithm. For each number in the sequence, we will take that many columns from the right and move them under the leftmost counters. So, for our sequence, we will take 7 columns from the right, all dots, and move them to the left. Then we will continue doing this for each number in the sequence. We take 2 now, moving them to the left. Then we have 2 more again, a bit of a boring sequence, I know. Once we reach a 1, we can stop. We will now read the pattern top to bottom, left to right, yielding the following sequence. Let's try this beat in FL Studio and it doesn't sound half bad. This is called a Euclidean rhythm, a rhythm utilizing the Euclidean algorithm to space out k beats in n time steps when k is not divisible by n. From now on, I will represent these algorithms with ER, number of beats, number of time steps. So the rhythm we just had would be ER 7/16. You can also easily introduce a phase, meaning moving the beats right in the time steps. For example, the previous rhythm with a phase of 1 would look and sound like this. With a phase of 2, it would sound like this, and so on. Once you construct one rhythm, you can phase it any number of times as long as you preserve the distance between the beats. From now on, I will be describing these phased rhythms with an additional number in our previous notation, thus having ER, number of beats, number of time steps, phase. Interestingly, if you take ER716 with a phase of 4, it sounds awfully similar to a very famous bass groove. Yes, Radiohead did make use of a Euclidean rhythm in their national anthem, most probably unintentionally, as the paper came out several years after the Kid A album. Toussaint discovered in his paper that many traditional rhythmic patterns can be described as Euclidean rhythms. For example, ER71613 is a very typical samba pattern called partido alto. If we try with different numbers, let's say ER374, we have the Bulgarian Rachenica.
The tempo could differ. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3.
The paper goes over a ton of examples of traditional rhythms, being Euclidean ones. I won't go through each of them because then we'll be here until tomorrow. I'll link it in the description for you to read it for yourself. Anyways, if you enjoyed this video, please consider liking and subscribing. It is a bit of a different style of what I usually make, but hey, I think this fascinating relationship between music and math, beyond just pitch and timbre, deserved to be described. At least for me, this was interesting as somebody who has to deal with both music and maths on a daily basis, but the latter mostly out of necessity for work, but oh well. I might make more videos like this in the future, who knows. Subscribe to stay tuned, and I will see you in the next video. Bye.